So good evening, everyone. This is a live session. We thought this is a good place to discuss a lot of things. So I think what we are doing is we will discuss a couple of more conceptual things of radio astronomy in terms of last week we covered radio interferometry at great length. Few things are still remaining, so we will cover that before we proceed. And now we break up this particular today's live session. It will go up to 2 hours, but first hour is we'll go through some more details of the lecture. This everything will be captured and put up in your course feed, and will be available. And slides also will be available. There was a little bit of a mishap that we missed the first few. We couldn't post, or it was not. Up to date till week 7, week 8, and week 9 will be up to date today. And so, in case there is any issue about the assignment of week 8, please let us know. We'll take it up in the second half. So first, we will have this discussion about the concept. After an hour or so, the TA Aperture will come in and show you exactly where all the materials are available one by one, and go through that. Then again, come back after that, the second half of next hour, and pick up some problems. But in between, you can keep posting and let us know if you have any particular problem with the week 8 assignments. Okay, we can go through that. As we discussed that we will have these sessions, live sessions every week from now onward till the end of this course, that we can get a direct contact with all the students and please bring in all the issues, etc. So let's begin with that, and let's see if anybody has a question. Okay, so Asha, are you there?
Yes, sir.
So we can also maybe in the next when we start after we finish this, after maybe you can also discuss a little bit about the forum questions and any issues they have with the week 8 assignments. Okay.
Yeah, sure.
Okay. So just to capture again, we showed that this is we have the single dish, and we know that for a single dish, this happens to me. For a single dish, the size of the dish, capital D, is basically the main thing. So lambda over capital D is kind of measure of something called the resolution. We have done that. As the wavelength becomes higher and higher, the size becomes impractical. So we started something, shifted to something called radio interferometry, where now the single dish size can be replaced by the dimension of the array, or the maximum baseline, which is covered. So if this is B max, then the resolution of this array is given by is proportional to lambda over B max. And that's how we avoid the impractical design. We can make much smaller number of dishes. Many of them and the distance between the largest distance between any two antenna is kind of proxies for that lambda over t for a single dish. And the other part is the effective area, which we can take care of by summing up the area of all the individual dishes. So area of each dish, if it is stated as effective area, the total number of antennas, and this becomes total area of the project. This is with GMRT, we have discussed before. So we go on. So how this works, we have done it a couple of times before, but just for the sake of it, and as we go multiple times, things become more effective. So if you have two antennas, you multiply that. We are considering what the multiplying interferometry. So far. So as we consider a radio source coming from infinity or distant far away field, if it is moving in this direction to both the antennas, then it will appear faster in antenna 2 than antenna 1, and the additional path length converts to directly to additional time, which is given at b dot s, over c. And so this all have been done before. One thing is certain, that as the Earth spins, this source gradually moves and appears in this direction. So at a given another time, the rays will be coming first to antenna 1 and then to antenna 2. And then the delay has to be compensated in antenna number 2. So essentially, all this depends on the direction from where you're receiving the emission. So we did this, the entire derivation. We have E1 dot E2, the output from each antennas. We correlate them or simply multiply them, then do an average on time where the faster varying term goes to 0. All this has been done before. And you retain the slower varying term, or which is function of tau, or this delay. And that is linked with the baseline and the lambda. And that is finally linked with the Earth's rotation. Okay, so that was derived earlier. If you're looking at a single baseline or single pair of antenna, then it gives rise to something called fringe. The frequency of this is given by this thing in the bracket, and that's for 1. Okay. Now, sorry, just one more thing. I think we have done it already. It also depends on this quantity B. So you can say as the baseline becomes larger and larger, longer and longer, this becomes very fast varying term. The frequency increases and it becomes faster term. So for a single spacing, you have this kind of a fringe. For multiple spacing, you will have superposition of multiple of them. So again, the Bmax in this case for the maximum baseline is the resolution, and that compares with the resolution for a single dish. Okay. Questions? If you have any, you can stop me and ask it immediately. This is a session to interact with you guys, so I think feel free to interrupt whenever you can. You can just unmute yourself and ask a question whenever you feel it is going a bit faster or something which is not quite clear. Anything so far? Okay. So yeah. So for different sources at the different spacing, you see different fringe. So we can just go ahead. Okay. So just a little bit of a different treatment. We introduce something called Van-Sitter-Zernike theorem. What is it? Now, what you have is that so assume any astrophysical phenomena occurs at a position of R on the sky, and it causes a time variable electric field. Since the source where this electric field originates is in the far field, we assume a convenient location over a celestial sphere of radius R centered on the telescope where it gets recorded. Okay, so you have at a distance, far away distance, there is some astrophysical phenomena occurred, and it created some time varying electric field. Now, since it occurred at a distance of R, at R position on the sky, we assume a sphere that and this telescope at a distance of R where this particular event occurred. Something like borrowing the concept of the celestial sphere. Similarly, so assuming that the space within the celestial sphere is empty, so there is nothing between that astrophysical phenomena and the telescope, then you can write at for the coordinate system R, which is the telescope coordinate system, you can write the electric field which is measured, the electric field which is recorded is linked to the electric field which is which occurs in the sky. And they are linked by this equation, where this is nothing but a propagator. Don't worry about it too much. And just like this is how the far away electric field transforms into the electric field which is measured. We have done something similar earlier. Okay, where did we do? By the way, am I coming in fine, Pasha? I'm audible. Perfect.
Yes, sir. Clear.
So basically, we have done this when we decided, when we discussed the relationship between far field electric field pattern, and the aperture distribution. And we figured out that these two are linked by a Fourier transform. Go back to your distribution. Yeah, so these two are linked by a Fourier transform, and we have shown that for different kind of aperture, rectangular aperture, circular aperture, etc. And so the same thing, similar thing also is linked over here. So you have the field which is recorded on the telescope is just nothing but the electric field in the far field in the sky propagated out. Okay, this is the expression of that. Now, if I just go ahead, so this is a radio interferometer measures not a single field, but the product of the two recordings from two different antennas. So that gives rise to something called a visibility, okay, which is nothing but a product of two electric fields measured by two antennas, 1 and 2. Okay, so this is called the visibility function, which is kind of something like a spatial coherence function and directly related to the average Poynting flux, which measures the intensity of the energy flow of an electric field. Okay, and this gives you the proportionality constant, half epsilon 0 mu 0 there. So if I do that and I express this and I put this expression over here, I can see that this becomes quite cumbersome. So visibility, this spatial coherence function is linked to the integral of this epsilon capital R1 and eta, sorry, R1 and eta R2, and the two propagators over there. Now, we can, it is assumed radiation from an astronomical source is not spatially coherent. So this expression is equal to 0 if R1 is not equal to R2. If they're not coherent, then this correlation will become 0. So R1 has to be equal to R2. So if I replace that in the previous expression of this, I finally get an expression which is equal to this. So they originate from the same point. Then only they become correlated. Okay, coherent. So if I do that math, finally, after a few steps, you essentially give rise to an expression like this, where this is the visibility function. V is an integral of A and I and e to the power minus 2 pi, so and so. So if we just do the math, it will be supplied to you. Don't worry too much. Then you can see that slowly you're seeing that this expression over here is nothing but, if I can write, V nu is nothing but a Fourier transform of A nu I nu. Okay. That's what it says. Where A nu I nu is a definition of redefining this particular eta nu R square. This function is redefined in terms of A and I. Now, A and I have a significance. What is I? I is the original sky brightness. If you remember our first week or second week of lecture, we defined something called a specific intensity. So this I is nothing but linked to the specific intensity on the sky plane. Okay, when talking about the astrophysical sources, and A is nothing but the primary beam pattern, which is receiving this entire information. So V and is just nothing but a Fourier transform of A nu and I. You can also look into the detailed lecture, which also records this one. So that's essentially what we do have. Okay, now let's redefine the coordinate system on the sky in terms of something called direction cosines, L, M, and N. So L, M, and N has a relationship where L square is equal to M square plus N square is nothing but equal to 1. Okay, so two of them are independent, one is dependent on the other two, the value. So the two-dimensional image of the sky obtained from an interferometer is projection of the intensity distribution on the sky onto a tangent plane at S0 is equal to L equal to 0, M equal to 0, and N equal to 1, which is the center of the field. Okay. And so if you define that, we are coming to the geometry, then finally this d omega can be expressed in terms of dl dm over 1 minus L square minus M square, square root of that. You don't have to worry about this exact derivations, etc. Just remember the final expression that the V and the product of A and I are a Fourier transform pair. Okay, and this coordinate system on the sky represented by this direction S is broken down, is derived in terms of L, M, N, which are the direction cosines. That's an easier way to get it. So what we do is So if I start doing that, then we essentially define the coordinate system on the ground on telescope plane in terms of U, V, and W. Now remember one thing, that this direction S depends highly on the it changes position, right? And the rotation of the Earth kind of influences the projection of this baseline. So finally, all what we measure is in terms of a projected baseline towards the direction of the source. So if the source is rising in the east with the same interferometric baseline, we will have some kind of a projection compared to if the source is setting towards the west, then the projection will be changed. So essentially, for a same baseline fixed on the Earth, it sees the sky in a different way based on how the Earth rotates. Okay, so that has to be somehow accounted in when we define this coordinate system for the interferometry. Now that forces us not to just stick to the coordinate system of the antennas on the ground, which is expressed by X, Y, and Z. We have shown this earlier, so last week as well, where Xij, Yij, and Zij is nothing but the XYZ, Xi minus Xj, Yi minus Yj, and Zi minus Zj, corresponding to any two antenna pair given by Y and J. So that is fixed. However, the hour angle and the declination towards the center of the field is defined by H0 and delta naught. While delta naught does not change with time, as the Earth rotates, the H0 do change, because H0 is what? H0 is nothing but the RA naught minus LST. And LST do change as a function of local time. So as the source rises in the east and sets in the west because of the rotation of the Earth, the delta naught is fixed, but H0 changes. So for a given fixed baseline, you have multiple U, V, and W coordinates. Okay, and that's what we expressed in terms of the effect of the Earth's rotation synthesis, which we discussed last time also. Okay, so and also it depends on the lambda. That's a pretty neat derivation. So yeah, so we can skip this. Right. So if you're agreeing with that, then what we derived earlier, the V R1 R2 is given in terms of the Fourier transform of A and I, the product of A and I. Now, ideal case, you can assume that A nu as a function of direction is unity, okay? And then this expression becomes much easy, and it just becomes the Fourier transform of the sky. However, we know for a real antenna, A is not equal to 1 for any direction, and it changes because it has a radiation pattern, which is kind of looks like this. So as a function of theta and phi, the radiation pattern changes. So ALM is essentially has to be measured separately. So if we put all of them together and the actual values of actual expression of L and M, we can recast this expression on the top into this huge cumbersome expression in the middle. which is true for a three-dimensional sky, where there is no assumption about how much is the extent of the field of view, as well as it takes care of the curvature of the Earth and the curvature of the celestial sphere. For both of them, it is taken care of, and this is the total full expression at its glory, where the visibility or the spatial coherence function is nothing but a Fourier transform of the product of A, the primary beam pattern, and I, which is the sky brightness. That's the expression. Now, that becomes, this is not a Fourier transform, sorry, but it becomes a Fourier transform if we do a simple approximation of a small field. So the third dimension of W and N becomes negligible, and this expression reduces to just two-dimensional Fourier transform, where V is a function of U and V, no longer W. That can be ignored, and it is AI, A and I, the product of both, e to the power minus 2 pi I, U, L, and Vm. Okay, times dl dm. This is nothing but a 2D Fourier transform equation, and also known as the transited Zernike equation. It's a very powerful expression, and the main equation for radio interferometry, where we understand this is the correlation function, which is the output, spatial coherence function, which is the output of the interferometer. And that is linked with the product of the primary beam and the sky. So that gives rise to, if I do both it, I can write it here only. So if I can write the visibility V, I just drop everything else, is nothing but a Fourier transform of A, the primary beam pattern, multiplied with I, the sky. Now, the objective of the entire process is to understand how does the sky looks like. So to make an image of this eye. So that is easy, because now that becomes inverse Fourier transform of the V, right? If I know I, if I know V, I can do an inverse Fourier transform and get V. Okay, and if you know your antenna very well, you can have a prior knowledge of the I, which you can then divide from the image, and you get the final value of I. That's a very oversimplistic way of representing. But that is what to show is that the simple image which was coming for a single dish, that you just have a single dish. Remember that you have a single dish antenna, and you were pointing at different parts of the sky. You made an image by doing a raster scan. Try to motivate that. So if you had a single dish telescope, you have a single primary beam. So what you did was you have pointed in one portion, then pointed in the next portion, and the next, and the next. And you made this kind of a raster scan of the entire sky by pointing, right? And for each values you get something, and then you know that supposedly there is an effort to source at the back, which is like this. So you can sample this and get the image. That's what a single pixel camera represented by the single dish telescope, like green light telescope, for example. Okay. Here, things are a bit different. Here you have a bunch of antenna in an interferometric array, and you are getting visibility, which is a function of frequency, is a Fourier transform of A, which is the primary beam pattern of any antenna, times the sky. So if you have a priori knowledge from electromagnetics about this function, then you can, this is your observable, so what you observe or measure sorry, this is your measurement. This is your measurement. And this is come from electromagnetic theory. If you know your antenna very well, design very well, and this is finally your sky, which you are trying to image. So based on, this is not a single value because you have multiple baselines. So if you have n antenna, you have n antenna minus 1 divided by the number of baselines. Each baseline has different distance. So based on that, you have different values of u and v. So finally, you get that, and then you do the processing to finally derive the value of the image of I. Yes, Akash. Akash, you can go ahead, unmute yourself. Akash, you can, you raised your hand, Akash Kulkarni. You are not audible. Okay, maybe we can move on and we can come back. Maybe it's accidental. Okay. So let's move on. So one more thing we have to discuss is that as we showed, this is again the same picture of the VLA, and what we're showing over here is that for a shorter spacing, you have the fringe which is slowly varying, and for a longer spacing, the fringe varies much faster because the frequency of the fringe omega is proportional to the baseline. So as the baseline increases, the omega increases, and so that is pretty obvious. All right. So you have different kind of fringes. By looking at the fringes, you can say, you can compare and mention whether one is coming from a shorter baseline than the other one. Okay, this is a video. This is the animation which we have created and done in IIT Indore, one of my earlier PhD student. created this. And we have to go through it slowly. Yeah, okay, I got Akash's question. So he's asking the question that the question is about the ANU. Can I say it is the effective aperture or is it the FOV? Essentially, it is the FOV. Okay. It is the pattern, the far field radiation pattern, which we know we can characterize it in terms of the the far field pattern. You consider the half power beam width, and that is the kind of FOV. So I think you can consider that to be a FOV. That is fine. Okay, so coming to this expression, let it start from. Let me go back and forth. Okay. Yeah. So see, we will keep it running. It goes in the loops. Don't worry if you miss one frame. So on the left-hand side on the top, we have taken the sky or the eye. That is your eye. Okay. So this is your eye, nu, L, M. Okay. Just a point source. That's it. That's your model eye. We're simulating it. Okay. And this is your antenna layout. So this is your N antenna. And also we are showing how they are laid out. We are varying the number of the antennas from two antennas to 256. Okay. Oh, sorry, 512. And 512 has some significance. We can avoid that right now. It's not important for this, but it is close to some real antenna design eventually. So as the animation progresses, this N ant value goes from 2 to increases to 512. Very well. The topmost panel on the right-hand side is the UV coverage. What is that? Now we know that our values U, V, W is some kind of a matrix rotation of X, Y, and Z. We have done this earlier, right? So this is what the UVW coordinates are for, just a snapshot. So you're looking at one particular direction given by the sky position over here. That's your location. So you know which direction to look. So this defines your S, right? And you know your direction, so you know X, Y, Z. So just simply let the just a snapshot. So you're looking for each antenna, each configuration. You're just taking a snapshot. So you have the UVW values. So you can then do the visibility is a Fourier transform of I simply. So we took the visibility measurement by knowing the UVW coordinates and just inverse Fourier transform it to get the I. But see the difference. So as the antennas goes from 2 to a huge number, you see that the recovered image is finally coming close to what you actually see on the sky. Okay. So what is going on? So when you start from 2, you have only one fringe. Then becomes 4. So let's look at it again. Now start. So 2, then 3, then 4, then 5, and so on and so on. So when it was 2, the number of baselines was 1. When the number of antenna became 3, the number of more baseline became 3. Then 4, it increases further, and so on and so on. So as the number of baselines increase, the total number of fringe superposition of that also increases. And so you are able to recover the original extended elliptical Gaussian, which is the closest you can come to a point source. Okay. So that's the Fourier imaging kind of thing. We will post it again so you can keep looking. Let's go forward. So the visibility function and the sky brightness distribution are nothing but a Fourier pair. So your visibility V is nothing but a Fourier pair of the sky brightness I. Here we are assuming, just for the simplicity, that A is equal to 1. Okay, unity. It's normalized, completely flat. Very ideal case. It is not real. So for a point source, the as a flat function, DC. So this is brightness. I wrong. This is the brightness I, and it's the Fourier transform of V, the visibility, and we assume that A is equal to 1. Okay, so if the sky brightness is a point source, just the brightness in the center, then it becomes a DC signal, as we know by Fourier transform. We have done it earlier. There are 2 sources over here with so then it's basically gives a sinusoidal function. 2 sources far away, it gives a bigger function because now the distance is much more, so the frequency is increased. And if you have multiple sources with multiple different brightness, and you have a composite function which gives you like this. You have various different kind of sources, like an extended source looks like this, a Gaussian kind of a thing, and you have different kind of functions on the visibility. So yeah, so you have 2 different sources, extended sources with the distance that gives you a function like this, and so on. So you can have various different kind of pictures which gives you so you have a double source separated by a distance. What is this? If you refer 2 sources, this looks like similar. We'll come to that. So essentially, this is all nothing but a Fourier pair. The visibility given by this and the sky brightness. Here we write it in full glory again. That would be 2D Fourier transform. Okay, which assumption is that the sky is it's coming from a very small region of the sky. Okay, that's doable. So a few more things in this fashion. So we started from this expression. We have the UV distribution. What we can do is that you understand that so what happens is that if you have a fixed number of antennas, there are the fixed number of baselines. So it doesn't have a complete coverage in the UV distribution. It has discrete coverage. So in order to absorb that discrete coverage in the continuous integral, what we define is something called a sampling function. Now, sampling function is very simple. Wherever there is a UV value, the sampling function becomes equal to 1. And wherever there is no UV value, it becomes 0. So it's 0 or 1. Okay. It's just a mathematical way to absorb a discrete function into a continuous function, defining another function which is like a mask. You have a value at some positions, you do not have a value at some positions. Because this your finally the expression of your for expression for your UVW are these are fixed. Okay, they do not have all possible values. Given a set of x, y, z, we have multiple number of UVW, but still not all values. Okay, because it only can produce some set of UVW for all possible H nodes. Okay, not all. So it doesn't, even though it is a kind of a projection, but still it doesn't sample all possible values in UVW plane. So we still have some limited holes, as you see for this one. Even with 512 antennas, which is quite a large number of values, you still see a lot of empty space in the UV UV space. So UV coverage is still not complete. Hence, to account for that, we have a sampling function which gives 0 when there is no value. So if there's a gap, the sampling function S is equal to 0. And if there is a value, like for this particular position, you have a value. So for this or this, S is equal to 1. Okay. Then you can write still this one in terms of integral. So ideally, we would have loved the coverage in the UV plane to be continuous and complete. But because it is not, so we don't have an ideal response for the sky brightness. What happens is even a fixed compact source appears like a sink function, and we'll talk about it because of this missing coverage in the UV plane. Because we are not having a field aperture, we're having discrete antennas which can only fill certain amount of the UV plane and not complete. Okay, so that gives you something called dirty or incomplete coverage. And so it's linked in terms of a convolution. So original sky convolved with something called a PSF or point spread function. It's called point spread function. It will give rise to the first impression of the sky. So if you know the beam or this point spread function, you can recover the original sky. Okay. What this says is the original image, original measurement is not ideal. We have talked about now the measurement as we do the real measurement for an interferometer. The original measurements have some kind of a gain variations because we are finally getting measurements from two different. Remember that we have a simple receiver chain system for a single antenna, radiometer, and we have gain variations for the electronics. So this is the same thing. We are not having any different kind of system. Instead of having one system, we are having multiple systems. Previously, we have only one in an N system. We have an antenna, and we had some kind of an LNA to amplify, right? We have a down converter, a mixer to down convert, and then again a LPF kind of a thing to cut off, and then finally a spectrometer, etc. And okay. Now every antenna has a similar system. So there are electronics involved, which causes variation in the gain, in frequency, and time. So ultimately, that will affect the visibility which is measured. The observed visibility is nothing but some kind of a gain for each of the antennas times the true visibility. So that is taken care of in terms of something we call as calibration. Please watch the video, original lecture video for this bandwidth thing. They are expressed in details over there. UV coverage we have already discussed, and so we will skip this for this particular session. Just to show you that if you're looking for a VLA like telescope, these are the UV coverage. And for a particular source, if you're looking at a source called 3C147 with a declination of 50, with an antenna which is looking from VLA. So VLA, its latitude is 34° north. Okay, and correctly check. Yeah, it's 34° north, and so this is the different for different hour angle. You can see different snapshots of UV coverages, and that will change. So UV coverage is a tricky business, and it changes as we look at different sources. So that was the source at declination of 50°, and with VLA being at 34°, almost looking at towards the zenith, little bit off. But now, if you're looking with the same array for a delta equal to 90° sources, like a North Pole, then you see something like this. If you're looking at 60, you're looking like that. If you're looking at -30, almost towards the south, this you see like something very weird pattern appears. This is because of due to the location of the array on the surface of the Earth, you can have different kind of projection towards different parts of the sky. Okay, so I stop here and put it over to Harsha for discussion on the material. We will take I will come back after half an hour and again pick up certain topics from the problems which were covered in this particular week. So over to you, Harsha. Stop sharing.